Good afternoon, I am Mr. Ish. Thank you for joining me. Looking here very quickly and at a good introduction of partial derivatives. Multivariable calculus topic here. You can have equations or functions which have more than one variable. If you want to do a derivative of one and keep everything else untouched or unaltered, then you're looking here at partial derivatives. The essence of partial derivatives is that you have the function of multiple variables. You do your derivative procedure on that one variable you are interested in, and everything else becomes a constant with regards to that variable. The nomenclature for partial derivatives is this: the partial derivative with respect to x or any variable you're interested in. The methodology behind partial derivatives is not hard by any means. It's an extension of what you already know with regards to derivatives, and the best way to show you that is by a number of examples. If I'm looking at this as a function 2xy, you know there are two variables x and y, but I'm interested in the partial derivative of x. How do I go about doing that? Remember what I said, you make everything else a constant and you do the derivative only of your variable. You are looking at this with regards to the 2y being pushed out as a constant, and now you're going to do just the derivative of the x, which is just a 1, and your outcome here, the partial derivative outcome of that would be 2y, and your answer would be good. You see how it is? It's not an entirely new topic by any means. It has all the same basic rules: chain rule, quotient rule, product rule, all of that. The derivative rules, the sum, difference, product, quotient, all of that. You're just doing it with regards to a single variable. Everything else becomes a constant in that entire procedure. Look right here. We're doing a partial derivative of this, 2x plus 2y. That right there is a sum of two separate variables, but what are we interested in? We look right here, which means everything else must become a constant. What does that mean? Well, if you want to look at you can say the derivative laws, you're essentially looking at this plus right here. You see, this right here is treated as a constant. All of this will zero out because the derivative of a constant is a zero. It'll zero out because you're not looking at the y variable in terms of partial derivative. You're looking at the x. There is no x here. It goes away. The only thing you're left with here is this. You're looking here at the derivative of this, and your answer would be just the 2. You can see we had the constant multiple property come into play, and we're looking at the derivative of that, the partial derivative. The partial derivative of this entire expression is just a 2, and now you're beginning to see that this topic of partial derivatives is not all that difficult. Now in the remainder of this video, we increase your confidence by showing you a variety. We're looking here at the partial derivative with respect to y, and my function is this, y divided by 2x. How can I demonstrate the partial derivative now with respect to y? Consider what I said, everything else becomes a constant. You're looking here at now 1 over 2x in partial derivative with respect to y of y. Because this 1 over 2x is being pushed outside. The derivative of this is a 1. Our answer here is 1 over 2x, not too hard, and the answer would be right. Now we increase the complexity just a tad bit. We're looking at the partial derivative with respect to y of this, sine xy. Now bring in the chain rule. If u is equal to xy, you can use that. Derivative or partial derivative with respect to u is equal to sine u, and then the partial derivative of that u with respect to y, you're looking here at xy. Now consider this, the derivative of this is easy, it's cosine u. We'll resubstitute the u at the end, but this is a constant, it can be pushed outside. You're looking at an x, and now the partial derivative of just y, and you know what that is, it's just a 1. When you rewrite all of this properly, you can push this x right over here, and then you're looking at x times cosine of u, which was just really xy, and this right here is your answer. The partial derivative of that function with respect to y is x cosine xy, not hard. How about this, the partial derivative with respect to y of e to the power of x over y? Again, it's a composite. U is equal to x over y. Then you're bringing in the chain rule. Partial derivative with respect to u of that original function is e to the u, and then the partial derivative of that with regards to u and the y, the variable you're interested in, you're looking here at x over y. But look, my variable of interest is a y, not an x. This x can be brought out here. I'm really looking at this x being brought entirely out, and then the derivative of e to the u is just e to the u. This right here is no more than you looking at the derivative of 1 over y. You can bring this up and bring it into an exponential form. You're really looking at y to the minus 1. You use a power rule, you're looking at minus y to the minus 2. That's what you have. Now I'm thinking in my head, I forgot to mention that the symbol for partial derivatives is this, modified d. You know the regular d, and now the modified d for partial. That right there is what you want to look at. Some people call it like the reverse or the flipped around 6. I like to call it like the slant d or a modified d. But that right there is a symbol for partial derivative. Anyhow, we have coming over here, remember this was minus y to the minus 2. Well, then you bring the minus out, you have minus x, you have e to the x over y square, and that right here would be your final answer. Again, remember this right here represents the terminology or the symbolism for partial derivatives. This answer here should be good. Minus x times e to the power of x over y divided by y square. What we can do is end the video with this question. It'll bring in the quotient rule and you'll see the chain rule. We're looking at the partial derivative with respect to x of this function cosine xy divided by x. You can do your f and g function. This here is my f function, here's my g function. You'll do the g function times the partial derivative with respect to x of that cosine xy. Then you'll do minus your f function times the partial derivative with respect to x of your g function divided by your g function squared. All of that, the quotient rule, you're familiar with that. This over here will bring in the chain rule. If u is equal to xy, we can do that. U is equal to xy, then you're looking at the partial derivative with respect to u. And then you're looking at cosine u and then partial derivative of that u with respect to x. We have xy minus cosine xy. The derivative of x is just a 1. We can be done with that over x squared. Now all you have to do is complete it. The derivative of cosine u is a minus sine u. That minus will come over here. You'll have a minus x sine u. Resubstitute the u x y. Right here, when you're looking at the derivative of this with respect to x, the y can be treated as a constant. This y can be brought all the way out here. The x will go away. You're looking here at a y and then minus cosine xy all over x squared. I want to write this out in a good manner and I will. Minus xy sine xy minus cosine xy divided by x squared. There's no need to isolate the minus and bring it out and then you distribute it across. You don't have to do that. If you wanted to do that, you could, and your answer would evolve into this. You'd have an xy sine xy plus cosine xy all divided by x squared. Either of these answers is good, but keep in mind here the xy component is part of the composite function sine and cosine, but here the xy represent two distinct separate functions. All of that has to be kept in mind, but that right there, it brings us to the end of this partial derivative video. Thank you for watching.